Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to the channel Chandan Physics. In this video, we are going to discuss derivation of various laws from Planck's law. Let's begin. In that session, we have discussed how various laws regarding blackbody radiation spectrum can easily derived by using Planck's law of blackbody radiation spectrum. The laws are WEIN'S distribution law, Rayleigh-Jeans law, Stefan-Boltzmann law, and finally WEIN'S displacement law. These laws are derived from Planck's Planck's law of blackbody radiation. As we have already discussed, Planck's law in terms of frequency, E nu d nu is equal to 8 pi nu square divided by c q d nu into s nu divided by e to the power s nu divided by kBt minus 1. Again, Planck's law in terms of wavelength, E lambda d lambda is equal to 8 pi s c divided by lambda to the power fifth e to the power minus s c divided by lambda kBt d lambda. That expression for Planck's law of blackbody radiation in terms of wavelength. By using any one of these equation, we can derive various laws proposed by various scientists regarding blackbody radiation. First, we derive WEIN'S distribution law. How to derive WEIN'S distribution law? For lower values of temperature, if temperature is very low, then the term lambda into T is small. Now, the exponential term e to the power s c divided by kBt. E to the power s c divided by lambda kBt is very greater than 1. So that we can ignore that is S, we can ignore sorry to say, Planck's law in terms of wavelength is not that expression. That is not the expression. Here E lambda d lambda is equal to 8 pi s c divided by lambda to the power fifth 1 divided by e to the power s c divided by lambda kBt minus 1 d lambda. That is the expression of Planck's law in terms of wavelength. Now, in that of denominator side, as that quantity is very greater than that of 1, we can neglect 1, so that we can ignore 1 in the denominator of Planck's law. Denominator of that of Planck's law expression. Therefore, E lambda d lambda is equal to 8 pi SC divided by lambda to the power 5th. In that of denominator side, we neglect 1, so we obtain 1 divided by e to the power SC divided by lambda kBT d lambda. So, E lambda d lambda is equal to 8 pi SC divided by lambda to the power 5th e to the power minus SC divided by lambda kBT d lambda. This one is the expression for Wien's distribution law, which is Wien's distribution law. Wien's distribution law. Next, Rayleigh-Jeans law. Same concept. For bigger values of temperature, the term lambda into T is large. Now, the exponential term e to the power SC divided by lambda kBT is equal to, we can expand as 1 plus SC divided by lambda kBT plus 1 by 2 SC divided by lambda kBT whole square plus dot dot dot. Higher terms are neglected, higher order terms. Only exist terms 1 plus SC divided by lambda kBT. As we write, neglecting the higher order terms. That is e to the power SC divided by lambda kBT. Therefore, E lambda d lambda in that of expression of Planck's law in terms of wavelength is equal to 8 pi SC divided by lambda to the power 5th into 1 divided by 1 plus SC divided by lambda kBT in terms of e to the power SC divided by lambda kBt, we write 1 plus SC divided by lambda kBt minus 1 into d lambda, or E lambda d lambda is equal to 8 pi SC divided by lambda to the power 5th into, here 1 cancelled out, plus 1 minus 1, we obtain 1 divided by SC divided by lambda kBt into d lambda. Therefore, E lambda d lambda is equal to 8 pi SC divided by lambda to the power 5th into lambda kBt divided by SC into d lambda. That is nothing but the expression of Rayleigh and Jeans law, which is Rayleigh-Jeans law. By using the concept of lower values of temperature, we prove Wien's distribution law, we derive Wien's distribution law from Planck's law, and again by using the concept of bigger values of temperature, using that of Planck's law, we derive Rayleigh and Jeans law. Next, Stefan-Boltzmann's law also can be derived from that of Planck's law. How we derive? Let the total energy inside the hollow enclosure that enclosure contain that black body radiators, and that hollow enclosure have all possible wavelengths. Is given by the total energy E is equal to, that is integration from the limit 0 to infinity, the energy density, that is E lambda d lambda. Therefore, E is equal to integration from 0 to infinity. Now, the value of E lambda d lambda is put from that of Planck's law. E lambda d lambda 8 pi SC lambda to the power minus 5th divided by e to the power SC divided by lambda kt minus 1 d lambda. That is the total energy inside that of hollow enclosure having all possible wavelengths. Now, it can be transformed to that of all possible frequencies. The above expression for the total energy density E inside a hollow enclosure can also be expressed in terms of all possible frequencies. That is, the frequency range from 0 to infinity, nu from 0 to infinity. Thus, we can write that energy density E in terms of frequency. Either we can substitute in place of lambda as nu is equal to c by lambda, or Planck's law in terms of frequency expression can be used. We can easily write it by using Planck's law in terms of frequency. So, E is equal to 8 pi h divided by c q integration from 0 to infinity nu q divided by e to the power h nu divided by k t minus 1 d nu. How to solve that type of integral? To solving this, putting h nu by k t is equal to x. Therefore, d nu, differentiating it, we obtain k t by h dx. Now, the expression can be transformed 8 pi h by c q in place of nu, that is x k t divided by h, means h divided by k t. Again, in place of nu, that is h divided by k t, in place of d nu, k t by h dx. Overally, k t divided by h, sorry, here q, then another for d nu to the power 4th 0 to infinity x s q, that is e to the power x minus 1 dx. Okay. That substitution is put in that of integral. Now, 8 pi h divided by c q k t by s to the power 4th 0 to infinity x s q dx, a minor change, e to the power x taking common 1 minus e to the power minus x. Is equal to 8 pi k to the power 4th t to the power 4th divided by c q 1 h, here 1 h cancelled out, that is h to the power q 0 to infinity x q e to the power minus x 1 minus e to the power minus x to the power minus 1 dx. In simple sense, since E nu d nu at the frequency range of that energy density is always a positive quantity. Means e to the power h nu divided by kt is greater than 1, or simply e to the power x h nu by kt, we substitute x, e to the power x is greater than 1, hence e to the power minus x is less than 1. Therefore, 1 minus e to the power minus x to the power minus 1 can be expanded binomially. 8 pi k to the power 4th t to the power 4th divided by c cube s cube integration over 0 to infinity x s cube e to the power minus x. Now we expand it binomially as 1 plus e to the power minus x e to the power minus 2x up to dx. To solve the type of integral, we use the standard integral. Using the standard integral, integration of 0 to infinity, that is summation, let m from 1 to infinity x s cube e to the power minus mx dx. That type of integral result as summation over n from 1 to infinity 6 divided by m to the power 4th, where m is an integer. M is an integer. M is an integer. That expression now change to 8 pi k to the power 4th t to the power 4th divided by c cube h cube into that expansion result as 6. Here e to the power, these terms are multiplied, that is 6, first term 1, next term 1 divided by 2 to the power 4th plus 1 divided by next term 3 to the power 4th up to continued. That standard integral formula is used to solve that one. Therefore, 8 pi k to the power 4th t to the power 4th divided by c cube h cube into 6. That summation term is, this is the standard integral result, and that summation results, since summation over m is equal to 1 to infinity 1 divided by m to the power 4th results as pi to the power 4th 90. That is a standard mathematical result. That is a standard mathematical result. Mathematical result. In that of series expansion, that result as pi to the power 4th divided by 90. Entirely E is equal to 8 pi to the power 5th k to the power 4th divided by 15 c cube h cube t to the power 4th. All these terms pi, 8, k, c, h all are the constants, K Boltzmann constant, C velocity of light, H Planck's constant. All such constants are the Stefan-Boltzmann constant sigma T to the power 4th. So, we derive Stefan-Boltzmann's law from that of Planck's law. This is Stefan-Boltzmann's law. Next, Wien's displacement law. Wien's displacement law can be proved, can be derived by using Planck's law. From the graph, when we plotted the graph by taking Wien's displacement law, the maximum energy at some value of wavelength lambda m at the maximum wavelength. Therefore, for wavelength is the maximum wavelength, then its differentiation with respect to that lambda, E lambda is equal to 0 at maximum, at maxima, that first order differentiation will be 0, or d by d lambda, the value of E lambda from Planck's law, E lambda is equal to that much 8 pi SC, 8 pi SC divided by lambda to the power 5th, lambda to the power 5th into 1 divided by e to the power SC divided by lambda kt minus 1. Its differentiation is equal to 0. How to calculate its differentiation? As you differentiate with respect to lambda, another terms are constant, 8 pi SC as constant, 8 pi SC as constant. Then we treat that one as first term, this one as second term, differentiation of first term, second term as constant, and then differentiation of second term and first term as constant. First taking that one, this one as constant, its differentiation minus 5 lambda to the power minus 6, this term as constant, e to the power SC divided by lambda kt minus 1 to the power minus 1. Next, differentiation of this term, that one as constant, minus lambda to the power minus 5th e to the power SC divided by lambda kt minus 1 to the power minus 2 e to the power SC divided by lambda kt SC divided by kt minus lambda square is equal to 0, is equal to 0, or this term multiplied to that of 0, then in that bracket term if minus is multiplied on both sides, then we obtain 5 lambda to the power minus 6 e to the power SC divided by lambda kt minus 1 to the power minus 1 is equal to these terms to this side minus this term as SC by lambda kt. If we use SC by lambda kt, SC by lambda kt lambda to the power minus 6 lambda to the power minus 5 lambda square, that is lambda to the power minus 3 that is minus lambda to the power minus 2. So, lambda to the power minus 7 divided by lambda, as a result lambda to the power minus 6, therefore that can be changed to this one. Okay. E to the power SC divided by lambda kt minus 1 to the power minus 2, then e to the power SC divided by lambda kt. On the both sides lambda to the power minus 6 lambda to the power minus 6 cancelled out, and e to the power this and e to the power that, only one exists. Therefore, 5 is equal to SC divided by lambda kt into e to the power SC divided by lambda kt into 1 divided by only one term e to the power SC divided by lambda kt minus 1. But we calculate it at maxima at lambda is equal to lambda m. Here putting lambda is equal to lambda m at maximum, that expression is equal to 5 is equal to SC divided by lambda m kt to the power e to the power SC divided by lambda m kt into 1 divided by e to the power SC divided by lambda m kt minus 1. Here let me putting SC divided by lambda m kt is equal to x. Therefore, we obtain x e to the power x minus 1 is equal to 5. When we put SC divided by lambda m kt is equal to x, then that expression will be changed to this one, and solving this we obtain the value of x is equal to 4.965. Therefore, in that of expression, SC divided by lambda mkt, SC divided by lambda mkt is equal to 4.965. We have to calculate what is the value of lambda m into t. So, lambda m into t is equal to SC divided by 4.965 into k. So, all the constant, value of Planck's constant 6.62 into 10 to the power minus 34. Next, speed of light 2.998 into 10 to the power 8 divided by 4.965 into Boltzmann's constant 1.38 into 10 to the power minus 23. Solving that entire mathematical terms, we have lambda m into t is equal to 2.898 into 10 to the power minus 3, lambda its unit meter, temperature units Kelvin. Lambda m t is equal to 0.002898 into 10 to the minus 3 as this one meter into Kelvin, that term as a constant. Therefore, lambda m t is equal to B. B is nothing but Wien's displacement constant. Therefore, from Planck's law we derive Wien's displacement law. This is the expression of Wien's displacement law. Wien's displacement law. So, here with the help of this video lecture we understand how to derive various laws from Planck's law. Derivation of laws from Planck's law. Planck's law in terms of frequency, Planck's law in terms of wavelength, Wien's distribution law by taking lower values of temperature, lambda t is very small. Then that Planck's law changes to this one, which is nothing but Wien's distribution law. Next, for bigger values of temperature, lambda t is very large. On treating that one, we derive Rayleigh-Jeans law from Planck's law. Next, Stefan-Boltzmann law. Total energy inside that of hollow enclosure having all possible wavelength. Then that expression changes to the expression in terms of frequency, and finally we derive Stefan-Boltzmann's law. Next, Wien's displacement law. Similarly, for maximum wavelength, its first order differentiation result as 0, proceeding like this, and for the value of x, that is 4.965, that expression holds good. Putting that value, we obtain the constant, that is Wien's displacement constant, and finally we derive Wien's displacement law from that of Planck's law. So, with this useful and informative notes, let me wind up the session. Thank you.